Okay, let's talk about intramolecular bonds. Specifically, I want to talk about covalent bonds. Okay, so what are we going to look at? We're going to look at polar and non-polar covalent bonds, talking about the application of electronegativity in finding that. Then making sure that you know how to, when you see one, pick out whether or not a bond is polar or non-polar. Okay. So covalent bonds, what does that look like? Now imagine that each of these bonds is talking about electrons. So these dogs have electrons each, but then what they can do is they can come together and they can share those electrons. Now the sharing those electrons here is what we call a covalent bond. So each pair that's shared, that's one covalent bond. And the reason why we want to do this is more stable, have a full valence shell, full outer shell. Okay. Now the sharing of electrons, you know that covalent bonding is sharing of electrons, but that doesn't mean that are not, I should say not here. So that doesn't mean that you're sharing them evenly. Okay. Some of the elements attract those electrons better than others. And we've talked about this because it's about electronegativity. So if I have two atoms and they're both trying to pull upon that shared pair of electrons in that bond, one of those atoms is actually going to be able to pull that electron or the shared pair of electrons closer to itself than the other. And that all depends on electronegativity. So when you're looking at polar and non-polar bonds, you need to look at the two atoms and think, okay, what are their electronegativities? By the way, you don't have to memorize it. You don't have to memorize the Pauling scale or anything like that because it'll become really obvious really soon. But by definition, if they differ in the Pauling scale by about 0.4 to 1.8, now that 1.8 value could vary depending on what source you're looking at, but as a general rule of thumb, it's going to be a polar bond. So that means that the electrons will actually be hanging out on with one atom more so than the other. So you can imagine mostly anything that's going to be bonded with fluorine, which is the most electronegative element in the periodic table, is probably going to be polar. So here's an example. Hydrogen and chlorine, right? Hydrogen is much more electronegative than, chlorine is much more electronegative than hydrogen. So what that means is that pair of shared electrons in that bond, it's going to prefer to hang out with the chlorine, right? So it's going to pull itself closer to the chlorine, which exposes the hydrogen. The only thing that hydrogen has left at the moment is the proton in the nucleus. As a result, the chlorine side is going to have a partially negative charge because it actually does have that shared pair of electrons hanging out closer to it. The hydrogen side is going to be partially positive. So as a result, we've got two different poles. Because that's the case, it's polar. We call it dipole. Okay, so we've got polar and non-polar. Look, to be honest with you, as I mentioned, don't memorize the Pauling scale, just know this. You know that Foncl, F-O-N-C-L, are the four most electronegative elements in the periodic table. So if anything is really bonded to F-O-N-C-L, it's usually polar, except when it's bonded to itself. So here, if it's F to F, as an example, that's not going to be polar because the strength of each of these atoms to be able to pull the electrons closer to itself is the same, so it cancels each other out. However, you've got hydrogen fluoride. This is going to be partially negative, this is going to be partially positive. Why? Fluorine is much better at pulling the electrons closer to itself, right? So if these electrons closer to itself than hydrogen, even better than chlorine. So polar versus non-polar bonds. Sorry, polar bonds versus polar compounds. Now, just because you have a polar bond doesn't mean you have a polar compound. But in order to be polar, you have to actually have a polar bond. So there needs to be an overall tip or an overall sort of side, I guess, where there's an overall charge, a positive side and negative side. So, for example, water. The bond between each oxygen and hydrogen is polar. Oxygen is much better at pulling the electrons closer to itself, which leaves hydrogen a bit more positive, oxygen a little bit more negative. If you actually have a look at the shape of the compound, in general, this side here is more positive, this side here is more negative. Because you've got these two poles in the molecule itself, we consider this as polar. Okay, here this is non-polar. So for this structure here of methane, it's going to be non-polar because everything's non-polar. However, this is the unique one. Carbon dioxide. Each bond between the carbon and the oxygen is going to be polar. Oxygen is going to pull the electrons closer to itself versus carbon. However, when you put it together as carbon dioxide, it's going to go this way, it's going to go this way. That carbon is not really going to overall go anywhere. And so overall, there's no sort of this side's positive and this side's negative, right? And therefore, this is a non-polar molecule. Another way we can look at it is like vectors. So this here, actually, like the extent of the arrow is actually kind of showing you, hey, where's the negative charge? So it's more negative going this one, positive, so positive, negative. So you can see here, overall, these vectors actually cancel each other out. Whereas with water, you have more positive, negative here, more negative here, positive here. And overall, there's a more negative charge towards this way, positive charge towards this way. You can see that these vectors don't cancel each other out. Therefore, it's a polar molecule. So, polar bonds. Okay. Polar bonds occur, the electrons are unequally shared. Why? Because the electronegativities of the elements involved are different. Okay. Non-polar bonds have an even-ish sharing. So you can have maybe less than 0.4 and it's still considered as relatively non-polar, no poles. We use this symbol to indicate, hey, this side of the bond is a bit more polar, negative, this one's a little bit more positive, but we use it as partial. So this here, delta, means it's partial. In general, as a general rule of thumb, anything that's bonded to Funkel, usually polar, unless it's itself. Okay? And remember, you can have polar bonds, but not necessarily they have to be polar molecules, like in the case of carbon dioxide. So, thank you so much for hanging out with me today. I hope it was helpful, and always remember, no matter what anyone says, yeah, you can.